virtual conference. And we are super excited to have Chris Magwood here tonight. He's going to talk about the Beam carbon calculator. So here I go. I'm sharing my screen.
It's going to go smoothly.
Oh yeah, it's be great. Practiced it 20 times here. I wonder how I go to the next slide. There you go. So a little bit of housekeeping just as we get going. Well, I guess everyone's muted as they come in. But if you have any questions, just put them in the chat and we'll get to them at the end of the talk and we'll answer all the questions. We're not at the AGM. This is just a slide left over from the other night. But if you are doing this for a continuing education sort of thing, put your email in and we will get back to you with those details. Big shout out to all our sponsors. Super happy to have them participating and their help with all this. And so thank you very much. And if you can support them with a project that you're working on, please do. And so just a land acknowledgement as we get started here, and that sort of weird thing, we're all scattered all over Ontario, but just take a moment to think about the land and our impact on it. We're mindful of our impact on the land and acknowledge the privilege we have to build here, and encourage you to learn more about the land you live on at nativeland.ca. Just a personal note on that one. I think it's a little bit on all of us to think about how that impacts us in a personal sort of way. But, so we build here in Lanark County, and generally the land is, old, pasture, or, maybe like a lake that's been opened up because of a logging road that's been built or something. But basically the land is untouched, except it was logged maybe 100 years ago or something. And so when we get to it, we are the first big impact that the land has ever seen. And it's a huge responsibility. And for all of us that are here, we're all builders and architects and designers, and it's a huge responsibility that we carry forward to, the next generation and to the land itself. And we have to do as good a job as possible to build good structures. And with that, I'm going to pass it on. Oh, I gotta go back a slide now. I don't know how to do that. I'm going to pass my screen on to Chris, and he will take control and tell us all about Beam. Oh, how do I do that now?
Or I could do my Tim Cron impersonation and attempt
that'd be good to see.
The envelope of natural building with my best Tim Cron impression.
Claire, how do I make him have his screen now?
You have to click on the stop sharing screen.
Oh, okay, there we go. Sorry, everybody. I'm tech bad.
And then
and click on you.
I need to find me. There we go.
I'd like to see his impression too, Tim.
Well, I know the only thing I could really do to do a Tim Cron impression would be to like start being really warm and sweating, which doesn't come naturally, but that would be my go-to Tim Cron impression if I could pull that off. Okay, hi everyone. It looks like people are still rolling in, so that's great. I'm really happy to be here to be presenting this to you. It's really exciting for me and our small but awesome little team that's been working on this tool over the last couple of years. And when I present here at the ONBC, I'm sure some of you have seen David Eisenberg present. I think he actually came to an ONBC conference once, but he has this great line about how sometimes we feel like, oh, are we spending all our time just preaching to the choir? And I think a talk like this to me sometimes feels like, oh, is that what I'm doing? But he always reminds people that you actually also need choir practice, and that I'm really appreciative for the amount of opportunity I've had in this group to sort of, think things through and say things in front of a friendly room and sort of hone the message and sort of get better, a better choir gives a better performance. So I thank you for all the other opportunities I've had to practice this stuff in front of you, and now you're kind of first in line for this beam presentation too. So I think probably I can't see everybody's name now that I'm presenting, but I probably know most of you, and you probably know me, and so you probably know that I'm not a software developer by by training or inclination, but I have been a sort of design builder in Ontario for quite a long time, 25 odd years. Some of you may recognize some of the buildings here that I've been involved with. Some of you may be sitting in one of them right now, I don't know. But anyway, over the years, I've had a really great chance to work with so many good people and forge so many great relationships while working on these buildings. And just before I got on tonight, I was moving something around on the bookshelf, and this little beauty kind of slipped out, and I was like, oh, yeah, I've been kicking around the ONBC long enough that there's still an original copy of the information package for building officials lying kind of half under the bookshelf. So so I guess I'm going to try to lead into the sort of why we're even bothering to make a tool to look at the carbon footprint of building materials. And for me, it comes out of the care that all of us have had for a really wide range of issues around buildings. I think in this movement, different things attract people, and people have sort of different reasons for wanting to think about different ways of building. But essentially, there's a bunch of them, and it could be you're really into energy efficiency, it could be you're really into resilience, it could be you're really into affordable building, it could be that you want really great indoor environment quality. It might be all of those things, but there's sort of this set of criteria that we've all kind of built up around our practices to figure out, what is it that we're trying to achieve, and how do we know when we're achieving it? And I think in my sort of own practice, and then with Endeavor Center, we worked really hard to come up with metrics for all of these things, and figure out, could we actually measure if we were doing these well, how well we were doing them, and sort of find places that we could maybe make improvements. And then I was working on a book in 2014 called Making Better Buildings that was all about all of those different criteria, and trying to look at all of the different building materials that were out there, conventional ones, alternative ones, and sort of assessing them according to that whole list of criteria. And as I was researching that book, I came across a little tool, I guess, a little spreadsheet that had been done in the UK called the Inventory of Carbon and Energy, the ICE database. And as I scanned through, I was like, oh, this has a whole bunch of different materials in here that I didn't think a list like this would have. And it actually even included straw as an insulation material, and gave a carbon footprint for straw. And so as I was putting that book together, I was like, well, I just stumbled on this information. I might as well put this in the book too. And by the time I had compiled all of that at the end of 2014, I showed up at must have been the 2015 ONBC annual general meeting. And I'd had some time to sort of digest some of those embodied carbon numbers I'd found, and to start doing some back of the envelope kind of sketches in terms of what they meant. And it was kind of blowing my mind. I called it at the time the carbon elephant in the room. Some of you might have been there for that presentation with this little elephant character. But that really sort of opened up the rabbit hole that I've kind of been going down ever since. So at that early presentation, I had done these little sketches of a prototype kind of 1,000 square foot little house, and taking embodied carbon data from the ICE database, from basically anywhere I could find it. If there was a hole, I went searching, and I was just kind of putting whatever results I could find together. And what was becoming sort of really interesting was how different the exact same house could be in terms of its carbon footprint from its materials. So anything from a building having, like in my first calculations, oh, this one has 10 tons of carbon associated with the materials. This one has almost none. This one bumps up to 13,000 tons. Hey, look, this one that was made with straw walls actually has sort of net carbon storage. I was just kind of a bit blown away by this climate impact that I hadn't sort of seen or been aware of, and amazed that a house, the exact same house plan and built to comparable levels of energy efficiency and stuff could have this huge difference in its carbon footprint. And so that seemed very sketchy, back of the envelope-ish, in terms of whether those numbers were for real, whether I was doing that properly or not. It certainly seemed a little incredible that you could have that much carbon footprint from materials for a little building. So with the great assistance of my colleagues in Endeavour, who sort of gave me the space to go back to school, I went back to Trent and did a master's degree where I kind of looked at all of this in a lot more depth. And through that process, I showed up at the ONBC gatherings a few more times, and finally with some sort of results in hand from that study that I did with my master's. And it turns out that what had been sketched out in 2015 looked to pretty much be the case in 2019, with a whole lot more rigor. With a lot of really great people in the embodied carbon space kind of looking over my shoulder and helping me out, and really making sure that my methodology was on point. But it turned out that, yep, sure enough, the exact same building. So the numbers you're seeing here are for a little small 4-story apartment building, but the same building built to the same level of energy efficiency could have these crazy different results. Could have 240 kilograms of emissions per square meter, or it could be net storing 137, or land anywhere in between. And all along, the thing that continued to stand out was that if the better your result was, the more likely it was that you had a whole lot of natural building materials involved. So, sure enough, this great carbon storing thing over here on the right, has straw and wood fiberboard insulation. It's got compressed straw interior wall panels. It's got, like lots of different natural materials, fiber-based materials. And it turns out that the carbon those things store is meaningful on a house by house scale for sure. And so those results seemed interesting enough and possibly impactful enough that I wanted to kind of take them and sort of publish them out in the world in something that wasn't just a 100-page thesis document that nobody was ever going to read. And so in 2019, the ONBC was by far the most generous sponsor of this white paper that we put out as Builders for Climate Action. There were a number of other sponsors, but that support sort of allowed me to take those thesis results and turn it into a more legible, digestible, and an interesting report to talk about all of this in the wider industry. And one of the things that was included in that report was some extrapolation about, you know, the study was all about individual buildings, but what did this look like if we kind of expanded it out to the wider low-rise residential sector? And in this case, this is US stats, but you know, essentially what looked to be the results for business as usual type buildings, the materials that make all the low-rise residential buildings in the US appear to contribute about 54 million tons of emissions to the atmosphere every year, which is about 15 coal-fired power plants worth of emissions. And yet on the other side, if we could kind of get people to move to other materials, more natural-based materials, fiber-based materials, carbon storing materials, we not only have the ability to not make those 54 million tons of emissions, so we can make that go away, and we can go sort of further and you know, store a whole bunch more, basically put the emissions of 10 coal-fired power plants a year out of the atmosphere and away and into our buildings. And you know, obviously this is just low-rise residential construction just in the US, and so if you start to think of this scaling out, it got really exciting because it felt like, well, here's one of the ways we help fix the climate. It's not a matter of, oh, how do we incrementally, you know, make a 10% reduction or a 20% reduction in emissions, or, you know, slowly by 2050 push to zero, but then we still have to get a bunch of carbon out of the atmosphere. It's like, no, this is a solution. And one of the interesting things about being one of the people presenting this solution is that I was able to say, you know, these buildings that we're talking about, these carbon storing buildings, they're not imaginary, they're not theoretical, they're not something that, you know, we could R&D for the next 20 years and then figure out how to build them. It's like, this is what me and my colleagues do. You know, there's a whole bunch of these things all over the world, and a whole whack of them right here in Ontario that even if they were built without this as the intention, there's a whole bunch of buildings that sort of stand there as testaments to the fact that that this carbon storing building stuff is doable. So the report did generate a whole bunch of interest. Got asked to do a lot of presentations and speaking gigs and conferences and things like that. It was super interesting to see how, in particular, folks who've been in the energy efficiency field for a really long time, who, you know, cared deeply about the climate and hadn't thought about it through the lens of material related emissions, but had only thought about it from operational emissions. The stuff in the reports that kind of compared the impacts of the two, I think, you know, it definitely popped a lot of people's minds. It made people really think differently, and it shook up quite a few of the conferences that we presented at, and I think, you know, in a really good way. And so that led to some offers and some ability to do some studies for people, and so the studies were great because it sort of gave us a chance to look at the results beyond just the kind of model buildings that I had imagined in that first paper. But in order to sort of do these studies at a larger scale, needed a much better tool to be able to do them with. My little cobbled together spreadsheet that I used to do that thesis project, it's pretty laughable when I look at it now. You know, it did the work. It it did what I asked it to do. I kind of fumbled through and made something that was functional, but it certainly wasn't going to allow us to, easily enter, all kinds of different buildings with all kinds of different, materials and assemblies and stuff like that. So we started working on making that a more robust tool. And that is what sort of led to Beam, which just had its just launched publicly a couple of days ago. So it's been a sort of wild and interesting arc to get to the point where this tool is now something that that anybody can go and download and start to use. And it wouldn't have happened at all without this sort of great team. I say on the screen here, it's a magical team. It felt magical because it, now that we've kind of pulled this off, it seems clear that we couldn't have pulled it off without this particular, group of people with their particular skill sets. I don't know how everybody kind of, ended up in the right place at the right time to make this happen. And, big shout outs to Eric, who I think is in the room today. So pop on the screen earlier. How often, do you find somebody with natural building experience who also happens to be an engineer and who also happens to have a really good background in software development right around the time that you're trying to develop a tool? So it's really, his involvement in the project has been invaluable. Melanie came on a little more recently, but she has used Beam over and over and over on lots of the studies and has provided so many great insights into what the tool needs to do, what it doesn't do, where the roadblocks are, and really helped it become something so much more user-friendly than it wouldn't have been without that. And Jen has been incredible in keeping Endeavour and Builders for Climate Action moving and afloat and energized and legal and all of those kinds of things. And also just so many creative ideas and again, impossible to imagine all of this happening without her. And I think some of you will probably remember Jacob Rakusin. He's been up and presented at ONBC a few times, but he's been a really great colleague through this whole thing. We did a lot of our sort of early presentations together. He actually did all the energy modeling for the operational side of my my thesis study for me, and he continues to have really great input into the work too. So I wanted to just take a minute and really acknowledge these people, because I often get to be the one standing here sort of talking about the tool and presenting it in public, but it does not exist without all of these folks. So when the tool was kind of ready and we'd done some studies and we had a team, we got some results. So the three studies that we've worked on in the last couple of years, one was for Natural Resources Canada. And there we studied 190 model homes that they gave us. So like my first study, these were sort of based on actual plan sets, but they weren't necessarily real houses, but they were at various levels of energy efficiency in various cities across the country, and some different typologies: single family, bungalow, 2-story, and a row house. And again, when we started applying materials to these models and then looking at the emissions factors for those materials, we ended up with results that looked an awful lot like my initial results. So finding that you could have really high carbon footprint for materials like 513 kilograms per square meter. That's half a ton of emissions per square meter of floor area. So, it's, there's just no way that we do anything to help the climate if we're building at that kind of level of emissions. And then a kind of middle of the road result that landed around the 150 mark, which was higher than my middle of the road result, But I think, we chose materials that we really thought reflected a kind of standard practice that we were seeing in the industry. And then, at the lower end, a really great result of 2 kilograms per square meter, which is, almost a zero carbon building. And that's from using the best available materials. So this is not things like straw bale. This is things like cellulose insulation, wood fiberboard insulation, linoleum flooring. So things that maybe not all builders are using, but that, are on the market and code compliant, and that, everybody should be able to use. And then again, that great sort of carbon storing example on the right is when we applied things like, straw bale walls and hempcrete basement insulation and, all kinds of other natural materials to those same models. We would end up in net carbon storage territory. So, that was really great. That really, between that and using the energy models from those buildings that Enercan provided us, it really made the case that in most parts of the country, the materials were going to be the bulk of that building's carbon footprint for at least the next couple decades, which is when we really, have to do something about the climate. And in provinces with, fairly clean electrical grids, that it might take 100 years or more before the operating emissions add up to what the material emissions might be. So that study was great in that it really lit some fires in the federal government level. I'll show you some of the results of that in a minute. But again, these were all model homes, and so just as we were finishing up the Enercan study, we got a really great offer from the city of Nelson, BC, to do a study there where we would be looking at as-built homes. So they were working with an energy advisor in BC. Everybody has to now do a HOT 2000 energy model as part of their building code submission. So actually an ex-Endeavour student was involved in doing all those energy models out there. And so we applied a version of the BEAM tool that we built out for Enercan that actually connects to the HOT 2000 program. And this was our first time sort of, being able to do real homes. So this wasn't us making up, material palettes that somebody might build with. This was just actually how people were building. And what was interesting is we got, at least at the high end, very similar results to what we were getting in our models, including, a worst case scenario of over 300 kilograms per square meter, an average result that actually landed, right in exactly the same spot as our Enercan average did, and a sort of best in show in Nelson and Castlegar of 72 kilograms per meter squared, which was pretty great for an actual building that was not designed to be a low carbon house. And then to the right here, this one that has 2, that house wasn't actually part of the study in Nelson, but it came to the attention of the energy modeler partway through the study, and she thought that it would be really interesting to run this one through the estimator tool because it seemed to her that it would have a really great result, and sure enough it did. And interestingly, it had the kind of result that we predicted a builder could do if they used all the best available materials, and that's in fact what this builder did, and they got exactly that result. So great proof in the Nelson study that there's so much that we can do, even if natural building doesn't take the country by storm in the next couple of years, that we can still help builders figure out a way to get to pretty close to zero carbon footprint on the material side with things that are at hand and affordable to them. And then the last study we just wrapped up recently for the Greater Toronto and Hamilton area. And this one, we looked at 503 as-built homes in the region. And you can sort of see that, again, at the high end, there's the house on the 500 plus kilograms per square meter. So Indeed, it's not just theoretical that people might be building at that kind of level. It actually is happening. The average result was a little bit higher than in the previous two studies at 189 kilograms per square meter. And the best result in that study was 116. So, not as low as it was in Nelson and Castlegar, but still really great to know that, at 116 kilograms per square meter, that builder, who's a tract builder making lots and lots of houses, is able to make that house, affordably. That's their current best practice, and it had nothing to do with trying to make a low carbon house. So, when I look at the difference between the average and that, and think, wow, you can make a house with 40% less carbon footprint just by doing what this builder is doing, and they're not even trying yet. It sort of points to how much low-hanging fruit there is out there for the low-rise industry to be able to make some really serious reductions really quickly. And so the exciting thing is not only are sort of builders and people in the natural building world these results are leading to actual things happening in different levels of government. So we're working with Vancouver right now to help them map out their low-rise embodied carbon reductions. They want 40% reduction from today's baseline by 2030. And so BEAM will be part of sort of helping them assess what those averages are now and what they need to be to meet that 40% reduction. The EMBARK study for the Toronto region has led to the Toronto Green Standard, the new version 4 that just came out this year. Now has an embodied carbon cap at the level 2, which is the voluntary level. But that means that in the next round of the Toronto Green Standard, that will become a mandatory level. And really exciting to see that, that we did the study, they saw the numbers, and, they were kind of incorporated in there quite quickly. And then the work at Enercan has been part of, a really interesting push that's happening there, such that just this December, Justin Trudeau's letter to the Minister of Natural Resources, one of the things that's being requested of them is that they make model building codes, including a net zero emissions building code that align with national climate objectives. So what that means is, the next version of the building code is not going to be about energy and energy efficiency as the kind of unit of performance. It's going to be about emissions, and it will very likely have both operational and embodied carbon emissions as part of that. So, and this is just a few places where this is happening. It's taking off in lots of other parts of the world, around North America in particular, and in Europe. But it's really, exciting to have seen this kind of go from what felt like pretty fringe research 5 years ago to, potential, national government action here in Canada on it. It's really it's beyond any kind of expectations I would have ever had when I was standing in front of you all talking about a goofy carbon elephant in the room. So I'm going to now tell you a little bit more about the tool itself. That was kind of the story arc of, where did it come from, and what the heck was I doing involved in making something like that. So there was the sort of impetus for making BEAM was we wanted to, really give people, in particular in the low and mid-rise residential sector, some really actionable information from a tool that's really easy to use. And so one of the things that was really critical for me, it's what really helped inform my look at this subject right from the very first until now, is basically being able to line up, different materials for different assemblies side by side and see the carbon footprint of those materials, for that building, in that particular configuration with that, thickness or R value or whatever the dimension has to be, and yeah, just be able to line them up beside each other and get a really clear look at how different things stack up with each other. And then beyond just material by material, we don't really make things out of individual materials. We kind of put them together in assemblies. So, I wanted a tool that kind of built assemblies as its building blocks. So in Beam, sort of each of the main building assemblies has its own page, its own tab within the tool. And so, being a builder, I started it from the ground up. So it's like, your footings and your foundation slabs and things like that. And then your foundation walls, and then your exterior walls, and then your floor systems and your roof. And so you can kind of go through and just make assemblies if you want. You don't necessarily have to make a full building model. You can look at, you can build out 3 different versions of a foundation for a building and see what the comparative carbon footprint of those will be. And then also wanted it to be able to be used early on in design development to kind of help people understand the impacts of some really early decisions, like, does it make more sense to make a really wide flat bungalow, or does it make more sense to make a tall narrow 3-story building of the same footprint? So that too, you can in Beam, you can put in really general dimensions. You don't have to have a specific building plan. You can just sort of like play around with floor area, wall area, heights, those sorts of things, and start to see how that might impact the emissions. And then obviously, you can then take all of that and use it to build whole building models. And you can kind of iterate on those buildings. You can start with a baseline building. Hey, this is what I normally do, so let's have that be one model, and then let's go into that model and change a few things and see what happens, and keep iterating that way. So the tool has all of those sort of options built into it. It's not a complete model of a house. So the materials that you'll find in Beam are the main structural, enclosure, and partition materials. So everything that's got a little check mark here. So that's footings, foundation walls, insulation, exterior walls, roofing finishes, like floor finishes, wall finishes, ceiling finishes. Yeah, all the stuff that makes up the structure, enclosure, and partitions. And we sort of chose, might be not quite the right word. Those ended up being the materials in Beam because those were the materials that both had the best representation in the available data, and they also made up the bulk of the materials for a building. So in terms of overall mass, we're kind of representing the majority of the mass of the building. But one of the things that we really want people to be clear about when they use this model or this tool is that their model doesn't include a whole bunch of things as well. And so, we can't really use Beam to say, the carbon footprint of that building or the materials in that building is X, because we're not including things like stairs and millwork and trim and cabinetry. We're not including paints and sort of surface finishes. We're not including any exterior groundworks, driveways, anything like that. We're not including fixtures or mechanical, electrical, or plumbing materials. And so there's a pretty good chance for a lot of those materials, the reason they're not in Beam right now is because there actually just isn't really good data about them. But from everything that we can tell, they may be another 40 to 50% of the carbon footprint of the whole house. So right now, even when we're saying, oh, a building is a net carbon store, if we added all of this stuff to it, it may be that it's not even quite. So just want to be really clear that there's a lot that's in Beam, but there's also a lot that isn't. And we're kind of looking forward to, over time, being able to build out the tool as the data becomes more available to more sort of fully represent the full carbon footprint of all the materials. And so also, if any of you have sort of dabbled in life cycle assessment or started to look into it, you'll know that there's a whole bunch of phases that are part of the life cycle of building materials. So there's kind of the initial product phase where there's emissions from going out and getting the raw materials and then transporting them to a factory, and then emissions from whatever processes happen during manufacturing. And that's kind of the product phase, or it's called A1 to A3, A1 being raw material supply, A2 being transportation, and A3 being manufacturing. Then there's the stuff that most of us in this call tonight do, which is the construction part. So there's A4 is transportation from factory to your job site, and A5 is emissions that happen at the construction site itself. And then we've got obviously the use phase emissions, maintenance and repair, deconstruction and demolition, and waste processing and disposal. Of all of those stages, Beam is really just looking at this first one. It's really just looking at the product phase. We've taken to calling that material carbon emissions, or MCE, because it is sort of all about the materials before they become a building. And it might seem strange that we've limited the scope just to that. But the reason for that is that if you sort of look at them by impact in terms of their overall climate impact, the product phase of making building materials tends to have the lion's share of the emissions that product will be responsible for through its entire life. So it obviously depends on the material, but on average, anywhere from 65 to 85% of all the emissions that material will ever be responsible for happen in this product phase. And then you can see that typically transportation to site and site construction can be anywhere from 5 to 10% of that. Maintenance and repair, again, another 5 to 10, and end of life 3 to 15. Those are pretty vague numbers. That's kind of averaging all materials. Some materials are more heavily weighted in different areas. Something that needs more maintenance or replacement, more frequent replacement, might have a bigger chunk there. But this maps pretty reasonably to the majority of materials. And so, this is the big chunk of the emissions, and this is what we in this community are capable of influencing right now today. And we can make some really big impacts here. And these are the emissions that are going into the atmosphere kind of as we speak. The factories are making the materials that we're all going to put in our buildings right now for the buildings we're going to make this year and next year. So, we concentrate on this. We also concentrated on this because this is the most robust data set. The data that's collected from manufacturing facilities and harvesting facilities tends to be pretty accurate. It tends to be something that you can define pretty good boundaries around and count really well. And as things move on along the lifespan of the building, it gets a little more vague as to exactly how much is emitted and when and where. And the further along the life cycle you get, the less certain those numbers become. So definitely, either me personally or the Beam tool is not trying to encourage us to not think about getting materials locally, that it's not trying to think about how often do these things need to be replaced or what happens to them at the end of their life. It's just, if we're going to give builders really actionable numbers, it feels like this is the place to do it. And a lot of what comes later, both comes later in terms of when the emissions happen. So they're their importance to what happens to our climate is less drastic, and also we're less able to kind of predict them accurately. So, so we concentrate on these upfront product emissions. And then Beam is a spreadsheet-based software. It's built out on Google Sheets, and the whole thing begins with you putting in some basic project information so that you can kind of track your projects. We need some assembly and project dimensions from you. And so basically, one of the things that's going on in Beam is these dimensions that you give the software are being used to calculate material takeoffs for all the materials in the assemblies that come later. So, if you're telling us that there's, in this case, 74.3 meters of foundation wall area, and it's concrete, then later on in the program you tell us, hey, that's an 8-inch concrete wall. So then we've got 8 inches times 74.3 square meters gives us a cubic volume of concrete, and that's what we can apply the emissions factor to. So these numbers can be as accurate as you need them to be to build a really great model of a particular house, but they can also be very general. I will quite often, if I'm showing people talking about different types of assemblies, I'll just throw 10 square meters or 100 square meters in one of these categories and just use that as a comparative basis. So we tried to keep the number of inputs fairly minimal so that there wasn't a lot of extra work for somebody to have to do to access the information. And then the guts of Beam is that there are assembly pages. So starting with footings and slabs and moving on up all the assemblies. And so there's all kinds of different categories of material. So everything that you would need to say make an exterior wall is here. So you'll find wood framing, metal framing, timber framing, SIP panels, like every kind of material, including things like straw bale and hempcrete and stuff like that, by category. So right now you're sort of looking at the wall cavity insulation section. So you can see we've got some spray foam options, sheep wool, mineral wool loose fill, fiberglass loose fill, and for my 74.3 square meters at, I think I defined here R20, I can start to see, the difference between the carbon footprint of all these different materials, and not just the difference between types of materials, but even within material categories that, there's a mineral wool bat that's got double the carbon footprint of, all the other mineral wool bats. So, where a category has a lot of competition like that in it, you can not only figure out, well, which material do I want to use, but which manufacturer should I be going to if I want to be procuring something with the lowest carbon footprint. And so this is the continuation of that cavity insulation thing, and you can see we've arranged them. I'll go back a slide from the highest carbon footprint, and it kind of goes from high to low. And so, as we work our way down, suddenly here we're into the carbon storing insulations like hemp fiber wool, cellulose, wood fiber, hempcrete, straw bale. And so you basically using Beam is kind of, scrolling through the lists of materials for each of the assemblies. And when you find what it is you want to use, and, here I went and clicked on the straw bale EPD from the UK. I click it, the little the number here goes orange, and that now gets added to that assembly subtotal, and it goes to my building's full total. So you can, for every assembly, every material, you can sort of scan the carbon footprint of these things and build out assemblies to meet whatever kind of carbon footprint you have in mind. And so these are the different assembly pages. So like I said, footings and slab, foundation walls, structural elements is like for timber framing and post and beam and metal frameworks, exterior walls, party walls for multi-unit buildings, cladding, windows, interior walls, floors, ceilings, roof, and then there's a separate tab for garages. So you basically visit each of those pages as you need them. If you don't need them, if you don't have post and beam or you don't have party walls, you don't have to enter anything, but on all the assemblies that that are included in your project, you just go through and make your material selections. And then when you get to the end, you get some really helpful outputs. So here, this first one is looking at sort of the carbon footprint of each of those different sections. So each of the different assembly sections. So, you can look at this model really quickly and see, well, if I want to make a difference, my foundation walls, my garage, and my footings and slabs, that's where the bulk of the impact lies. So, there's no point in me, worrying about what my windows are or my floors are, or at least not as a first step, because they're kind of dwarfed by these other three assemblies. So that gives you some sense of what parts of the building, which of these assembly tabs you might want to go back and revisit to make improvements. It also will give you just a couple acronyms here that hopefully you'll get used to if you're working with BEAM. MCE is material carbon emissions, and that's kind of like the total emissions for the building. So that's the total kilograms of carbon dioxide equivalent that, if you totaled up all the materials you checked in BEAM, this is the total. And so that's really helpful in terms of that particular project and knowing what its overall carbon footprint is. MCI is material carbon intensity, and this is taking that net project emissions and dividing it by, in this case, the conditioned floor area of the building, or down here, there's the total floor area of the building. And so that's how it becomes possible to compare between buildings of different sizes. Obviously, if you're designing a 1,000 square foot house and a 10,000 square foot house, there's a pretty good chance that the MCE of the 10,000 square foot house is going to be bigger. But if you look at it by square meter or square foot, it may be that that overall the materials chosen for the bigger house might result in a lower material carbon intensity than the small house. Not necessarily, but that's the reason for giving that MCI, is it sort of gives us a metric that we can compare across different building sizes. And then the little scale here, it just gives you a line as to where your MCI lands, and the scale is kind of based on the studies we've done so far. So I showed you before that the average is somewhere between sort of like 150 to 190 is what we found in the studies. So if you landed there, you'd be showing up this way, and you could be either getting lower or higher than that. So the scale just kind of gives you a sense of how your building is doing compared to the other buildings that we've looked at to date. You also get this output that rather than just showing you the assemblies with the highest carbon footprint, now it's broken down by specific material. So you saw that the foundation wall was, had a really high impact in that first graphic. Now you can see that it's the concrete from that foundation wall that's playing the biggest role there. That the concrete for the footings and slabs happen to be next. Here we've got the brick on the garage is the next biggest one, and etc. It works its way down, so you can kind of pinpoint the materials that are causing you to have the highest carbon footprint. And then just to be fair on the other side, we also try to point out which materials were giving you the lowest carbon footprint. So if you do have any carbon storing materials in your building, they'll show up here, and you can kind of see here that that building had spec straw bale walls and cellulose in the roof and bamboo flooring. And so those kind of offset some of the positive numbers on the way to giving the building a whole total. So, you know, you could look here and see like which of these materials might I want to use more of, or, you know, how can I do more to bring my my overall carbon footprint down. And then Beam gives you a chance to sort of save projects and then iterate on them. So, you know, the data is kind of stored, and you can go back to certain models, and you can pick, you can sort of, you know, iterate on a model in a bunch of different ways. And then I think I'm just about through the slides here, but I wanted to show, you know, one of the things that you know happens with Beam and that Beam makes really easy is you know making that baseline model and then seeing what you can do to make changes to it. So what you're looking at here is a graph of one of the houses that had the highest carbon footprint from the Toronto study. So it had 81,000 tons of emissions associated with it, or 262 kilograms per square meter. So that was a fairly high result from that. And so what we did was we took that Beam model and we just started subbing out some of the materials that that had been spec'd for that and made changes. So we changed to a lower carbon concrete mix in the footings, foundation, and slab. We swapped out all the insulation that we could for cellulose. So that was used to replace XPS fiberglass and mineral wool in this particular model. We used wood fiberboard as the continuous exterior insulation instead of XPS foam, and that made another big impact. We traded out the brick cladding for an engineered wood cladding. And then here for the flooring and drywall, we didn't change the material type, but we just picked, you know, the material in that category that had the lowest carbon footprint. And so you can see, you know, that handful of changes made a 75% reduction in the carbon footprint of that house. So, you know, with the exception of the different look of the building because of the engineered wood cladding instead of the brick, you know, the house has all the same performance characteristics, same design, same number of rooms, you know, nothing really changes, but the carbon footprint goes down by a whole bunch. And you can see, you know, going down from 262 kilograms per square meter down to 66. And, you know, this is that sort of bucket of low-hanging fruit that we're really hoping, you know, Beam makes obvious to a lot of builders in the sector. And then I think maybe, you know, folks in this room don't necessarily need this slide, but one of the things that messages I'm really, you know, taking to builders is that we're not asking you to jump from what you're doing today to making straw bale homes. Like that's, you know, we know that that's a big jump, but, you know, I think as you can sort of see on the previous slide, like a builder could pick, you know, there's 5 substitutions here to get you from this to this. You know, if you made, you know, 1 substitution per year in your practice, within 5 years, you would be down to here, and that would be pretty incredible. So, you know, we're really clear on saying this is a planning process. This is something that you don't have to bite off and tackle all at once. You know, you can say, okay, well, Beam can help me find what the absolute worst offenders in my material palette are and just stop using them right away. Because, you know, that's pretty easy to do. Just get off the, you know, the very worst offenders. And then, you know, maybe you're at that moderate level and then, you know, figure out, well, geez, I've never done cellulose walls before, but maybe I'll try that out. You know, next thing you know, you're kind of in this this sort of low to zero carbon mode, and then hopefully we can you know, have more people going down this path at more different paces, and hopefully there will be more than a handful of us natural building nuts, doing this thing over here with the carbon storing buildings within a decade or so. And I think, we can really use our buildings to point the way to that it's not a fantasy, that's something that's achievable, and that, even here in Ontario, we've got a good, couple hundred. I don't know if anybody has kept counting, but there's at least 200 or 300 straw bale houses anyway in Ontario, and if you add the sort of hempcrete houses and straw clay places and other things like that, there's a really good bank of buildings that use some really great carbon storing materials that really point the way to a climate solution that's not just a little bit less bad. Once you cross that line into carbon storage, you're actually doing more good. You're actually, starting to take carbon out of the atmosphere instead of just putting a little bit less into it. And the IPCC has made it pretty clear that we need to be doing that on a pretty big scale. And there's nothing with more scale on this planet than buildings. It's where the vast majority of the material flows on the planet end up in buildings. And so if we can change those material flows from carbon emitters to carbon storers, we talk about the built environment as potentially the sixth big carbon sink on the planet. We do a lot of it. We're going to keep doing a lot of it as populations grow, especially in Asia and Africa. And it's a great place to be thinking about taking atmospheric carbon and storing it really durably in all the new buildings and all the renovations that we're going to need to do over the next few decades. So, second last slide. I just really want to thank the the sponsors we had. Beam was kind of completely funded from within Endeavor Center for most of its development arc. And as we got close to launch, we were definitely running low. And so these four sponsors kind of stepped up and gave us some support to help us get the tool together and across that finish line. And we really want to thank them for that. And if you ever have the chance to do any business with any of them, we would encourage you to do that. And yeah, just to finish up, you can find Beam on the buildersforclimateaction.org website. And so that you can access the tool from there. We offer some training courses coming up in May and June. So, it's a relatively easy to use tool, but there's especially as it's gotten more robust, there's a lot to it. And so we're offering some training courses to help people navigate their way around it and figure out how to use it. And we also made the decision to make Beam free. We really didn't want to have a paywall up in front of it. It didn't seem that, in a bit of a climate emergency that, putting something like this behind a paywall was a good idea. But, we really do ask people who are accessing the tool to support us, to make a financial contribution for whatever value it is that Beam's going to bring to your building and to your practice. We put everything we had into making it, and we're really hoping that our community and our industry will sort of pay that one forward and help us cover the costs and enable us to keep developing the tool, keep improving it, keep adding materials to it, and continuing to make it sort of part of the movement to decarbonize the buildings. And also just a note that the book that I co-authored with Bruce King, Build Beyond Zero, which is kind of an overview of the whole notion of putting carbon away in buildings and all the ways that we can do it. It just came out a couple weeks ago. And so if you would like to get a copy of that, it comes from Island Press, and the link is at the bottom of the page. And that's the end of the slides. And so I would be more than happy now to take questions.
Thanks so much, Chris. Thank you to you and your whole team. That's amazing what you all pulled off, and a really valuable tool. So questions. I don't know. I haven't really been looking at the chat.
We've had a few questions come up, but it looks like most have been answered. We have one from Lowell. Why is Rockwool so high in emissions? Is it still made from volcanic rock?
Yep, it is, but you have to melt the rock into a liquid form. And so most Rockwool factories do that. The older ones do it with coal, which is why you saw the one really high result from Owens Corning, but most do it with natural gas. And so it's still a whole lot of fossil fuel input to melt rock or glass or any mineral like that and be able to spin it into a fiber.
Anything else? Well, in the chat or any other questions in general?
Not
There-
seeing new come up.
There's a new one in here. It says from Michaela, thanks, Chris. Lots to think about. Just wondering, is there a transportation metric within the calculation? For instance, we used Glutex wood fiber board on a passive house in Wolf Island, shipped from Germany. It seems like it would be a big factor with respect to emissions. I guess
Yeah.
that could be said for some of the mechanics within the buildings too that seem to come from those parts of the world.
Yeah, it may be less of an impact than you think. Like when I've looked at all kinds of whole building life cycle assessment reports, so that do include transportation to site, and typically transportation to site is somewhere between like 3 and 10% of the total building emissions. So and that's from like a wide variety of buildings. I know that 475 did a really good analysis of, they tracked a shipment of Gutex from Germany to North America. And I don't remember the exact results, but the material, even if you took off all the transportation emissions, still had a sizable amount of net carbon storage. So it wasn't as much as I would have thought, and it's kind of surprising that it's not as big a driver as people would expect. The study of big buildings, like large Part 3 buildings in Ontario that happened the same time we were doing our Part 9 study, found the same thing. Again, I don't remember the number, but their A1 to A3 was up in the 80%, and the transportation to site was, in the 5-ish range. So, again, I wouldn't say don't think about it. And like if you ordered everything from Germany, that would probably add up. But, one thing from Germany and, a bunch of things locally, like it may not be as big a deal as you might think. One interesting point on that, though, is our friends at New Frameworks did look at their construction site emissions, and typically for small buildings, those are pretty low. Like we don't use a ton of heavy equipment or anything like that on small buildings, but they decided to add up the fuel from their workforce going to the building site. And it was monstrous. Like it was shocking. It far outweighed the transportation of materials to site. Like just, 3, 4, 5, 6 people jumping in a pickup truck every day and driving 15, 20, 30, whatever it is, minutes, one way and then back was one of the biggest carbon footprints in their entire project. So, and that's not something that like a typical LCA would even capture. But I would say rather than worrying a ton about where you're transporting your materials from, I would say worry about how you're getting your people back and forth to that site, because that may be a lot bigger in the end.
Scary.
We have another question from Organic Radical. Are there any new and exciting natural building materials coming out sooner or later?
Yes, I think there always are. There's so much going on in that space right now. The U.S. government just released a $45 million granting program for developing carbon storing building materials. So, you know, there's lots of really interesting things going on in that program. Probably the thing that I'm most excited about is mycelium-based materials. In particular, there's a startup in the US called Occamworks that has figured out how to grow the mycelium so that it has pretty good structural properties, and they're working on being able to replace wood framing with this mycelium material. So they have a material that grows in 3 days, dries in 1 day, and can do what a 2x4 does. And so
Wow.
that kind of thing gets really exciting. Things like, I'm trying to think of the name. Will Schrubar's lab is making in University of Colorado, the Living Materials Lab is growing aggregate with algae. And so they're able to make the sand that goes into concrete by having algae pull that carbon dioxide out of the atmosphere and carbonate it. So yeah, I think things like that. There's the place that's growing bricks in South Carolina. What are they called? I can't remember. But anyway, they put microorganisms into a bed of sand, and they feed them mostly urea, and they excrete calcium carbonate that glues the sand together, and they grow bricks. So I think there's this whole really interesting realm of building materials that don't even require us to go mess with the natural world, can kind of leave the forests alone, leave the stuff where it is, and actually, use biological processes to grow materials. That to me gets really, that's exciting. It's a whole new kind of paradigm. And I think that twinned with, the kinds of natural kind of earth-based and straw and hemp and, all of those kind of materials that we all really like. It gets really exciting to think about hybriding all of that together.
Awesome. We have another from Organic Radical, as well as Katie Rand, wondering if the application for BEAM can be used for renovations of existing buildings, applied as like energy retrofit, adaptive reuse, or is it just focused on new builds?
No, it's just a list of materials. So, you can pick the ones you need for your project and ignore the rest. So if all you're doing is, say, wrapping a building with exterior insulation and putting new cladding on, then you only have to go to exterior walls and pick an exterior insulation and a cladding. Or if you're also putting in new windows, you can pick from the windows. So yeah, there's no requirement that you have to pick, something from every category. So yeah, I think it's every bit as applicable to retrofits. And I really hope that, I think it has maybe even a bigger job to play in the retrofit world than it does in the new build world, because, our federal government is putting billions of dollars out right now to get people to energy retrofit their homes. And I know that when they choose the wrong materials to do that, there's no benefit to the climate. Like the government is literally paying people to make the climate worse in their program that's trying to make the climate better. Because, if you emit 20 tons of emissions to get a material to put on your wall that's going to save 3 tons a year, that's a long payback. That's, we're looking at 7-8 years. In worst case scenario, maybe 10, 20, 30 years. So, we're not going to fix the climate by making additional emissions now in the hope, 20 years later, it'll, finally pay itself off. So I think, I really hope it gets a bunch of use from people who are looking at retrofits.
Another question from Lowell. For air loss and heat loss and exterior walls, is there a significance between wood frame fiberglass versus solid masonry walls for detached houses?
Probably I'm not the right person to ask that question to. I will defer that to the building science background.
Okay, fair enough.
I'm seeing Adam has had a hand up for a bit, so maybe we could go to him.
Are large producers of guilty materials showing effort to diversify and start producing the carbon storing materials, or are those large companies working against these efforts with indifference or opposition?
Well, one interesting thing is that most of the materials with really bad emissions are the companies that have done EPDs. Like there's actually more EPDs for bad materials than there are for good materials. I think that's partly due to the fact that those materials come from really large manufacturers who have the budget to, get an EPD done, whereas, small manufacturers don't necessarily. I think there has been opposition. I was just on a call with a bunch of prefab wall manufacturers last week, and two of them said, oh, they've been pushing their suppliers for EPDs for a long time and they've really resisted, and now recently, like, both of them have come around and said, yep, we're going to do that, because they realize that people are making their decisions based on this. And even if you're not crazy about your results, like if you don't start showing up in places like Beam, people just aren't going to pick your material at all, because that's like, if you're given a list of options, you're probably going to pick from the list of options that's there. So I think more and more EPDs are coming out all the time. And another interesting thing that has really stood out for me is that an environmental product declaration has a 5-year shelf life. So, you get this assessment of your materials emissions done, and it lasts for 5 years. I don't think I've seen a case where when somebody's redone that EPD, there hasn't been an improvement. Like, by and large, companies, once they report, once that becomes transparent, they get motivated to sort of drive that down. Now, some of that is because of government regulation too, but in general, I think the beauty of starting to make these numbers transparent is that it becomes a sort of something that a business now has to do. Like, a business has to be in the game of trying to make their emissions look as low as they reasonably can in order to keep their market share. And I think as we see things like Canada's potential movement to a carbon-based building code, and cities starting to put caps on embodied carbon buildings, like those companies are just going to have to, I think, start playing that game. Okay. Except it's not really a game; it's kind of the survival of our planet. But it's I think once this kind of reporting, whether it's Beam or other softwares, once this becomes something that people are really familiar with, it's hard to go back. It's hard to choose those really high carbon options once you've seen it. It's like you can pretend that that it wasn't there, but once you've seen it, you can't really unsee it. And I think I see that happen with the builders and developers that we've worked with so far. Is once they kind of see the scale of impact that just a few small changes can make, they get pretty motivated to do that.
Awesome. We have a question from Jacoba. Lafarge has come out with an eco-packed concrete. The concrete is mixing in 30% to 100% carbon content. Does Beam have this type of range, and what are your thoughts on that?
Lafarge they continue to promise that they're going to put out EPDs for that range of concrete. To the best of my knowledge, they have not yet. I don't know that, I'm not sure that those percentage numbers are accurate. I'm assuming that they're working with Carbon Cure, which is a Canadian company that sort of provides the technology to inject CO2 into curing concrete. It's a good idea. it doesn't actually help the carbon footprint of the concrete that much, because right now the CO2 that's being injected is like manufactured CO2. So it's not atmospheric CO2, it's CO2 that's being manufactured in factory. So there's a whole bunch of energy input to make the CO2 that you then go inject into the concrete. So I think in general, the EPDs for concrete that I've seen that have carbon cure associated with it are, in the sort of like 5% less carbon footprint range, which isn't bad. Concrete tends to be the biggest contributor to the carbon footprint of buildings. So what we can knock off is great. If they could figure out how to do it with atmospheric carbon, I think it would be a lot better. But there are other things that you can do with concrete that get you bigger results for less, cost and less, input energy right now, like switching to Portland limestone cement, like using higher percentages of slag or fly ash or pozzolans like that. So, but yeah, you can see if you use Beam, you'll see that what we offer for sort of concrete options are the Canadian Ready Mix Concrete Association has sort of like a nationwide EPD. And so they specify a bunch of different mixes at a bunch of different strengths. And so we've kind of picked, what they've identified as the average, the benchmark average for the country, and, some options above and below that. So kind of like the best mix that they say you can achieve, the worst mix, and a few in between. And, hopefully as more concrete producers start making EPDs, again, that it'll get easier to pick the ones that have the best results.
Okay, another question from Anna. Does Beam have the ability to compare in a retrofit project the original emissions with the emissions after a retrofit is finished? For example, insulation, new windows, new roof.
Well, all Beam would show you is the emissions of the new materials. The emissions of the old materials, they went into the atmosphere when the building was built. So like, there's nothing you can really do about them now. So, typically with a retrofit scenario, it's not that the building had zero carbon emissions, but like there's nothing coming from them now. Like they happen when the building was built. So you're kind of starting from today's baseline of here's the building. If we rip off a bunch of stuff and send it to landfill, there will be emissions from that process. And when we put new materials into it, there will be emissions from that. So like typically you're not kind of comparing it to when the building was built.
Question from Lindsay. How is the data / EPDs kept current or up to date?
Well, right now it's kind of a manual process. Eric, Melanie, and I do scans. So, just before we put Beam out, we spend another week kind of scanning everywhere. And, on a regular cycle, we'll kind of keep doing that. Eventually, we'd like to hook up to the EC3 database, which is a sort of a big EPD repository in the US. And they sort of make that readily accessible. So we'll figure out how to connect to that so they can do the maintenance and upkeep of new EPDs. But as of today, it's about as current as you'll find anywhere, and we'll try to keep it that way for the next ongoing like months or years.
We have a request to add the new mycelium algae or other material manufacturers in the chat. I see there was a link added. I fear clicking it because it'll take me away from my setup. So I'm not sure if that is meant to answer that question. It's www.okomworks.com. Do you know if that's a manufacturer?
I would be glad to share some links, when this is all done. I won't be able to do it while I'm on here, but I can share with people. Right now, none of those things, with the exception of the biomason bricks, and even those, like it's nothing you're going to buy from that manufacturer this month or week or possibly year. Biomason is producing a bunch of its brick, but last time I talked to them, they had 2 years worth of back orders. So, you know, you just have to start your own mycelium factory if you want to build it soon.
Okay. Question from, where did it go? Just jumped away. From Jeff, says, just curious, how does Beam deal with lime, i.e. material that is, it takes up relatively high carbon inputs up front, but absorbs carbon over time?
Yeah, so we attribute basically all of its emissions that happen when you burn that limestone. So both from the fuel that you burn to heat up the limestone and the CO2 that comes out of the limestone. And we don't really account for the reabsorption of whatever percentage of the carbon comes back to the lime. It happens fairly slowly and at much less than 100% of what got baked out of the lime in the first place, which isn't to downplay that that's a great attribute. Like, you know, not very many materials that are responsible for CO2 emissions bring them back in, but you know, it's not going to be a make or break thing, especially over the next couple of decades. You know, for me, my motivation for Beam is like, we got 10 years, maybe 20 years to fix this. And, you know, the concrete industry is a great one for saying that now. They're like, oh, by the time a concrete building's done, it's absorbed 3% of the CO2 that went, you know, into the atmosphere. In 100 years, like, it'll have absorbed 3%. And it's like, okay, but that doesn't help us today. And so, you know, I feel like the same with lime. Like, it's a great benefit that the lime will reabsorb some of that CO2, but not enough and not quickly enough, I think, to sort of, you know, tip the balance meaningfully.
Okay.
And other people might really disagree with that, but that's
just to follow up to that last question from Jup, Michael is asking, for the straw veil example in the presentation, was the lime plaster indoor and out included in the scope?
There was definitely plaster included. Like, that's, you know, one of the, in the cladding options for both interior and exterior, there's a bunch of different plaster, including clay plaster, lime plaster, lime cork plaster. So yeah, there's a bunch of things in there. I don't remember on that particular model, but yes, it would have been, there would be a plaster included in those assemblies.
Question from Claire, is there any new progress on hemp blocks?
There are a couple US startups that seem to be talking about going into production this year. I don't know whether they will actually do that, but you know, they've been posting photos of facilities and posting photos of initial batches, you know, rolling out of their prototype machines and stuff like that. So it may be happening soon.
Another question from Jacoba. If there was one material you could demand a production home builder start to use, what would you pick?
Cellulose insulation. It's the most unglamorous rock star imaginable, but in all of those examples I showed you, where it's like, look, if you just use the best available materials in really conventional buildings, look at where we can get to. And the biggest contributor to that is subbing in cellulose insulation for, you know, walls and attics, which, you know, seems like, okay, it's cheap, it's everywhere, it's code compliant, it's got 70 years of history. It's not, you know, shouldn't be that big a leap for people to get there. It does still seem like one, but it almost sounds silly to say it, but you know, literally it's kind of that first step is that easy.
I'm not seeing any new questions pop up. If I've missed anything, feel free to send your question through again.
All right. Well, if there aren't any more questions, maybe we'll wrap up. Do you want to add anything else, Chris, or anybody else?
Just my, my thanks to the Beam team. I can see Eric on screen. Thank you so much. And thanks to this group for, doing what everybody does, for supporting the work that I've done. It's been a real, it's meant a lot to have a home team to sort of talk to present to be able to kick these ideas around with. And everybody here has done such great projects and contributed in really great ways to all of this work. So yeah, thanks to everyone.
Right on. Thank you. I'm just going to share my screen again here. I'll try to anyway. Oops, there we go. So that wraps up Chris's presentation for tonight. Thanks a lot to Chris for joining us and his awesome presentation. Thanks for your help, Winter. And thanks to everybody else on the board at the ONBC for setting this all up and getting organized. Everybody, thank you for coming. On Saturday, we have our final day 3 of the conference, and we're having a roundtable discussion with 5 excellent people. One of them is Tim, Aaron Walt, Jamie McCullough, Jeremy Clark, and Paul Dowsett. So that should be super interesting, and I hope you can all make it out to that. And I guess that's it.
We have one more general question. Where can we find the recording after this presentation?
That's a good question.
I'm currently downloading it to my computer, and I think it'll be one that'll go up on our YouTube channel, but give us a few days.
Great.
Thanks very much, everybody. We'll see you Saturday.
That was a great turnout, guys. Oh, where did Chris go?
Looks like he bailed.
He totally bailed. Oh, well. Dave, I ended up making you a co-host because I couldn't figure out how to unmute anybody. It was super weird.
Yeah, I don't know what that was. When I hosted last time, I just set it to like mute as they come in, and then people could unmute themselves throughout. So
Yeah.
I'm not sure why that setting got changed.
It might have been me. I was trying to figure